All right, so good morning again, everyone. So welcome to tutorial number 10, where we are going to talk about percolation, which is an important concept in physics in general. And before that, let me introduce the book of the day, which is called Nanoscale Liquid Interfaces, and which has been gathered by Thierry Dersu and Jean-Pierre Elmet. So it's a collection of chapters made by different researchers in the field of nano weighting, because today we can, for instance, study very small droplets that are, for instance, indented with carbon nanotubes, and you could look at the meniscus around the nanotube and look at the properties of either static or dynamic weighting with those techniques. So there is really an improvement in the smallness of droplets you can fabricate. There are plenty of applications to that, but on the fundamental aspects, it allows you to study really perfect weighting. The carbon nanotube is a good example for that because it's really without any defect on it. So you can really look at perfect weighting in very small samples. All right. So today we are going to talk about percolation, as I told you. So there is first, for the people among you who speak French, a very nice outreach article by Dejean. So please have a look. It's very easy to read and very fun. There is a more serious one by Dejean where he makes a connection between the percolation problem in stat phys and the elastic. Sorry, there is something in the chat. What is the book? Okay, the book is Nanoscale Liquid Interfaces. Please interrupt me orally. It will be easier than looking at the chat, if you don't mind. Again, there is something in the chat. Okay, thanks for the help, Delphine. So please interrupt me orally. It will be easier for everyone. All right, so I was talking about percolation, and there is this scientific article by Dejean this time, where he makes the connection between the percolation problem and the elasticity of gels. As we will see in a minute, a gel becomes elastic when several bonds are created between units. And at some point you have one big macroscopic bond, and therefore you have some macroscopic elasticity for that system. So there's a direct connection between that, and it has been discussed by Dejean extensively. So today we would like to discuss what we call the mean field theory of percolation, which is the one proposed by Flory and Stockmeyer. And we will detail it in a minute. The idea is to remove any complexity in the interactions or in the loops and the topography of the network, so that we can do some analytical treatment. And the result we will obtain, like for the Ising model in critical phenomena, we'll have the good qualitative features, and only slight modifications of the exponent and the functional forms might occur in realistic systems, but you still get the feeling of what is the percolation transition. So please take tutorial number 10 with you. That is called the sol-gel transition. It's in the Dropbox. And let me share the screen. Up the whiteboard here. All right. So first of all, what is percolation? So percolation here, we define it as an assembly of points. You can think about a network that is, for instance, this one. Okay, you have an assembly of points that you can call sites. You can call them monomers if you prefer, or units. And those bonds, they are a priori related between them due to the topography of the lattice by links. So those black things here, they are the links. But those links are not necessarily bonds. They are just due to the topology. They say that each object has a neighbor, a certain number of neighbors around, but those bonds are not necessarily activated. Now you can think about activated links that we call bonds, and with a certain probability P, you can transform those links into actual bonds. So connecting the monomers into dimers, for instance, or trimers and quadrimers, as you can see here, with a certain probability P. And there is, of course, the probability 1 minus P that some links are not activated. So this is a description of, as we discussed, gels, because you can have several monomers that will be suddenly connected by covalent bonding. And at some point, you will have so many bonds in the system that it will become a macroscopic elastic material with one big infinite molecule, if you wish. But it's also very important for the theory of information. You can think that there is an individual in society that has some neighboring friends and that can connect or transmit some information with a certain probability P. And when this information is transmitted, well, then there is a certain size, typical size for the influence region of that agent. And then you can ask the question, for instance, what is the probability for having the information reaching the entire society? Okay. So it would work for networks, graphs in general, for, I don't know, Facebook or internet. It would work the same. Okay, so what is the probability that you would reach the total internet network by randomly clicking on links or ads or whatever? Anyway, this is the percolation framework, and it was a hot topic several decades ago because people have noticed that there is a strong connection between this and critical phenomena. Especially near the moment where the percolation occurs, meaning that there is one big, infinitely connected molecule in the system. And that point resembles a critical point, for instance, in a Ising-like model. So we will discuss that today on a very simplified model. Okay. So now it's a bit outdated. It's not anymore a trend, I would say, but this is something which is common in science. You have big bubbles of interest that grow and then suddenly disappear because other bubbles are growing. Okay? So for instance, in soft matter, today there is an important activity around what we call active matter. And it's a kind of really active topic where plenty of researchers are gathering their efforts to solve an issue. Okay. All right, so let us start with the model. What we want to do, as I draw here, is to look at what we call Cayley trees or beta trees, which are the following ones. As I draw here, you have one monomer, each monomer, that is connected to a certain number Z of neighbors. Here, in my example, Z equals 3, but you have 4-order trees, 5-order trees, and so on. Okay, and so each of those points are again connected to 3 things. Okay, so you have a kind of network that goes towards infinity like this. The important aspect of those beta trees is that there is no closed loop, meaning that never this monomer will be able to connect to that one. Okay, that's a very important aspect. So people like to draw this as, you know, I have a grandparent, then some parent, then some kids, and each of those kids, they have some kids as well. And then you have a kind of family tree that is oriented, I should say, here, meaning that it's not possible that a grandkid would engender a grandparent. Okay. However, even though we talk about causality or direction, there is no direction. I mean, this kid could be itself the grandparent of this chain, right? But the important aspect is that there is no loop in this type of topology. And that is why it's related to a mean field model for percolation, because you neglect some complicated interactions there. All right. So let me take the tutorial. What is important beyond that? We are interested in the main distribution that we call N of P and capital N, which is the number of N-mers, and I will define that in a minute, per site, or per monomer. So N-mer is simply what we drew before. This is a monomer, this is a dimer, this is a trimer, this is a quadrimer, for instance. Okay, so the number of n-mers is the number in the entire system of molecules of size n. So here n equals 4, for instance. And you just divide by the number of sites to define this distribution. So this will be the typical distribution of objects for a given probability, okay, of activating, meaning of transforming this black bond into an orange bond, a proper bond. Okay. All right. And so the goal of the tutorial is to calculate that and eventually to go near the percolation threshold and see if there is some universal behavior there. Any questions so far before we start? No? Okay, so let us attack. So we'll start with a few preliminaries and definitions. So this is part number 1. And the first thing we want to stress is are the limitations of the model. So the limitation of the models is, as we said, there are no loops. And the second thing is that if you think about the particular case, for instance, where p equals 1, well, you have now your network that is fully connected. So all those black lines, they are actual bonds, okay? So those are really connected. And so if now you remove one bond, only one bond, you end up with a situation where you have two completely separated infinite chains. So you have two systems suddenly, just by breaking one bond. And this is due to this very strange topology, very particular topology, because in a realistic network, if you think about, let's say, a periodic lattice like that, like a crystalline version of a topology here, you see that if they are all connected and suddenly you remove one bond, well, it doesn't change anything. Think about a gel where everything is connected, and then you just remove one bond locally. I mean, the elasticity is the same. You have one big macroscopic object. You don't have two separate and independent objects. So you see, it's nice because you avoid loops and you can do some analytical calculations, but you lose a lot of important features present in realistic systems. All right, so first of all, we would like to define several quantities. So we will first start by defining what we call n tot for a given probability P of activating a bond. That is the number of finite size polymers, is the total number of finite size polymers per number of sites or monomers. So according to you, what is the expression of n tot? Based on the distribution we introduced previously here.
This is the sum of n of the npn.
Thank you. So we sum between one mers, monomers, and infinite mers, if you want, of n p equal n. Perfect. So we have, if we know that quantity, then we know n tot. So let us continue defining important things here. We would like to know the probability of a given finite size polymer to be actually an n-mer. Let us call that, I don't know, nn, for instance. What is the probability of a given polymer? So I take my gel, or my system. It's not necessarily a gel for now, but my system, which is the topology I've presented to you, with some activated bonds with a probability P. And I pick a molecule. Can be a trimer, for instance. What is the probability when I pick a molecule that it is actually a n-mer? Again, based on n.
That is n of n divided by n tot.
Yes, thanks. So for now, it's pretty easy, right? All right, so let us continue. So then we are interested in the weight density. So let's call it W, for instance. which is a function of P and N, which is the probability for a monomer to belong to an N-mer. So it's the number of monomers belonging to an N-mer divided by the number of monomers, or site. Site and monomers are the same. Huh? So what is this quantity? Well, the number of monomers, yes, please?
That's n times npn.
Yes. So the number of monomers belonging to N-mers is the number of monomers in one N-mer multiplied by the number of N-mers. So we are back to the number of N-mers per site, which is the number of N-mers per sites or per monomers. And we just multiply by capital N, which is the number of monomers in one chain. Okay, so far so good. Then we are asked to estimate the sol fraction P-sol. So it's question number 5. What is P-sol? So the definition of P-sol is the fraction of monomers that belong to the sol entity. So the sol is what is not the gel. So when you have a network, like the one we drew at the beginning here, all the monomers belonging to this red molecule here don't belong to the gel because it's a quadrimer. You have only 4 monomers in this molecule. And it's not a gel because the gel occurs when you have at least one infinite chain in the system. That's percolation. And suddenly you have a gel at that point. So all the monomers that are not belonging to infinite molecules, they belong to the sol fraction. And all the monomers that belong to those infinite-like molecules in the system, they belong to the gel fraction. So as if you have 2 phases in the system, if you want. Okay? So the sol fraction, based on what we said so far, is what, according to you? Fraction and probability is the same. Mm-hmm.
1 minus n top? No.
Not exactly, no.
1 minus sum of WPN, I think.
Actually, you are talking about, that's good. You're talking about the gel fraction. The ones who are belonging to the infinite cluster. I'm interested first in the sol fraction, which are all the monomers that are not belonging to the infinite molecule, so that are belonging to finite size molecules only. So it's the reverse to, okay? But I think we are on the same page. So P-sol is indeed, as you suggested, the sum over all n's of W. Because if I sum the above quantity over all possible n's, I'm actually counting the probability for a monomer to belong to a finite size polymer, okay? I'm summing over all possible finite size polymers. Despite I'm going towards infinity, every n is finite in this cell, okay? And as you said, the gel fraction, well, it's 1 minus the sol fraction because a monomer can either be connected to this infinitely long molecule or not connected to this infinitely long molecule. So by conservation of the number of monomers, I mean, the sum of those 2 probabilities should be 1. And thus, as you said, it's 1 minus the sum over W. Okay, so there was just the confusion between what is gel and sol, but this is only terminology. Are you on the same page? You agree? Yeah? Okay. All right, so again, a definition. So we will continue doing a few definitions here. The gel fraction, actually, it was the next question. And just to illustrate what is the sol-gel transition, or I mean, the percolation transition. Remember, the control parameter here is the probability of activating one bond. So it can be between 0 and 1. And at some point, you reach a threshold that we call the percolation threshold. when the probability is smaller than the percolation threshold, according to you, what is p-sol? And p-gel. So before percolation, it means that there is not an infinite chain in the system. So all the monomers, they belong to finite size polymers, right? And so what is p-sol?
0.
Again, same confusion between p-sol and p-gel.
Then 1.
Yes, p-sol is the fraction of monomers belonging to finite size polymers. So not to the gel. And p-gel is the fraction belonging to infinite polymers. Okay. So before the percolation threshold, when the probability of activating a bond is very small, there is no chance that you have an infinitely long molecule. So all the monomers you find in the system, they belong to finite size molecules. Either they are not connected, they are single monomers, and it's a polymer of size 1, or they are connected to dimers, polymer of size 2, and so on. But they cannot be connected to infinite polymers because you are precisely below what we call the percolation threshold. So p-sol should be equal to 1 until that moment, okay? And p-gel, by conservation, as you said, is 0. Now, when p equals 1, what do you think about those two quantities? Here. When?
Then p-gel is equal to 1 and p-sol is equal to 0.
Yes, so the red point is here, and the blue one, the green one is here. And in between, of course, it depends on the type of model you are considering. So the exact shape, we don't really know it, but it will do something like that, right? And I don't talk about the concavity. And of course, the sum of the two should always be equal to 1. So if I do something concave, this one should be convex here. Anyway, but you see the point. So before the percolation threshold, you have only monomers here. Then suddenly you start to create molecules that are longer and longer in size on average, okay? And at some point you reach a moment where in the system you create at least one infinite long molecule. Then suddenly you start to lose monomers that belong to finite size polymers and to gain monomers that are connected to this infinitely long cluster. And at the end, when all the bonds are activated, well, you have one single big macroscopic and infinitely long molecule at the thermodynamic limit. Okay, and so the percolation point is this one that we don't really know yet, but we assume that there should be a finite probability at which you start to percolate. All right, to give examples, you can think about Z equal 2 in the Bethe lattice. So in the Bethe lattice, Z equal 2 is a bit boring, is the trivial case. This is the minimum Z you can consider because Z equals 1 doesn't mean anything, the bonds are not connected. So Z equal 2 is the trivial case. Okay. So according to you, when is the percolation moment here?
At p equals 1.
Yes. When p equals 1, all the bonds are connected together necessarily. And suddenly you've created an infinitely long molecule because the system is infinite in size, as we usually do at the thermodynamic limit. Okay. In contrast, if one of those bonds is not activated, then you are not able to create a system that is infinitely long. Okay. All right. Not one. I mean a fraction of those. Okay, so let us continue with the definition before really addressing that important quantity in closer details. We would like to define now something that is now pretty familiar for you in the polymer domain, which we call the weight and number averaged size or polymerization index. So let us call them like that. So this is the average number of monomers inside a typical chain that you just pull, okay? But counted in a chain average version. Number average. We call that number average in polymer physics. Which means that you give the same weight to a trimer or a quadrimer, to n equal 1 or n equal 1,000. You have just a collection of different objects that have different sizes, or one dimer, one trimer, one 1,000mer, and so on. But they are all identical in the terms of weight. Okay, so the first one with n equal 1, you will say it's 1 with a weight 1, and the one with 1,000 monomers, it's 1,000 with a weight 1. Okay, so it's not counted in terms of mass, simply in terms of number of chains. So what is NP according to you? It's an average. So it's the average polymer size.
The sum over n with the probability npn over n dot p.
Yes, exactly. Which could be written differently so that everyone sees that it's really properly normalized. Remember, n dot is the sum over n. And all those summations, they are made for all possible n's from 1 to infinity. So again, this is 1 over n dot, if I just re-put the previous one. And the numerator, remember, what is the numerator? It's the sum over w that we introduced previously here. And the sum over, so w is n times n, as we wrote, and the sum of w is the solid fraction. So in fact, we have this relation. We are just doing this kind of catalog, and we are almost done, but we are doing a catalog of definitions and relations that will be useful in the following. So that's one option. It's the simplest one. When you think about averaging, you will just count the number of monomers in a chain, but you will average them by weighting the number of chains that represent that value. A more realistic way, I could say, would be to weight this by the number of monomers themselves, like by putting the actual weight. So this is what people refer to as the weight average fraction. And instead of having n, then you want the weight, and the weight is what we already introduced before, so W. And you should normalize so that it's a proper average here. Agreed? So now, before the distribution was the chain distribution, normalized, but now it's the weight distribution, it's the monomer distribution, properly averaged. Okay, so you can rewrite this differently. This is, we already know that this is related to n squared times n. If I replace W here by its expression capital N small n. And this is the p-sol fraction. So you see, in fact, you could revisit those definitions by saying this is where this is exponent 1 and this is exponent 2. So in fact, those are two moments of the distribution n, this distribution. Okay. So that is why we generally like to define the polydispersity. I call it rho, which is the ratio of the two, which is in fact the ratio between the weight average and the number average, so that you have this variance-like quantity in units of the average. So it gives you really the polydispersity, which is the fluctuations around the average value. So if you have a polymer, for instance, you might have very long chains and shorter chains because the synthesis is not uniform. And you would like to know what is the typical dispersity you have. Are you really pure and delta peaked in terms of sizes, or do you have a wide collection of sizes? Because if you have such a wide collection of sizes, I mean, all the properties, static and dynamics, will be completely affected if you have different sizes inside. It's a complex problem. So experimentalists that like to know what is the dispersity in their system. So it's a kind of the variance normalized. But it's the same for a gel. Now I have my network. I'm populating this with increasing number of bonds. So I'm creating more and more different sizes of molecules. I have some free monomers, I have some dimers, a certain number of those. I have 1,000 mers, and so at some point. So I have a kind of assembly of animals with different sizes. And for me, it's important to know what is the spreading in those numbers. Is it really uniform, or is it from 1 to infinity very broad? And this is an important quantity, especially when we will reach the critical point, the percolation point at some point. Okay. All right. Am I done with everything we wanted to discuss? Perhaps we can take an example. The special case, for instance, where you have a very peaked distribution. Let me take it here, example. When you have a peaked distribution, you expect something like a certain n star, which is the value at which the size is peaked, and you put a norm. So this norm is because when n is equal to n star, NPN, remember, is the number of n-mers divided by the number of sites. So now you're in a situation due to that Dirac where you have only n star mers. Okay, for instance, n star is equal to 3. You only have 3 mers in your gel. Only, I mean, not in your gel, in your lattice. Okay, so you only have 3 mers. So you, of course, those 3 mers, each monomer here is divided by the size of the chain, so by 3. So you should divide by 3 here to make sure that you don't overcount the number of n-mers per sites. Okay. So let's take this example and the previous formula. So what is NN? So NN is the number averaged. So it's p sol over n tot. So what is p sol in this case? Do you have some gel?
There is no gel. We only have a finite size
Yes.
polymorphic.
Yeah. So due to that distribution, we are just populated by, I said 3 mers, but here n star mers, finite size polymers. So the p sol is equal to 1, and n tot is, remember the definition, is the sum over all possible n values of n. So we end up with n star. So when you number average the polymerization index, you get n star because it's peaked. It's really, there is only one possible value. So it's as expected. Same for W. So for the weight average, the definition is here. So it's the number squared times NPN summed over all possible n values divided by the solve fraction, which is again, so there was a solve fraction here at the denominator, which is again 1. So you only have the numerator, and plugging the Dirac distribution with n star at the denominator, I get only 1 n star at the end. So in this very pure system where I know exactly that everything is a trimmer, for instance, well, whatever you take, either the weight average or the number average, you get the same result. And therefore, the dispersity, which is the ratio of the two, is 1. So you are really monodisperse when it is equal to 1. Now, if there is some polydispersity, the polydispersity will become larger than 1, as you knew from your polymer courses already. All right, I think that's it for the definitions. Now we will attack more interesting aspects. So let us switch to part 2. Do you have questions on the definitions? Any questions? No? So now we enter the business. We would like to discuss this important quantity, PC. Does anyone have an idea on what is PC? No? So let me just consider, for instance, finite size polymers again. So I take a grandparent. Okay, and I'm taking z equal to 3 just for the drawing. Okay, so this grandparent has a kid, it's the parent, and then this parent has 2 in this z equal 3 case children, 2 children, and then you have grandchildren 2. Okay. Okay, and so the gel could be viewed as an heredity problem. I would make sure that there is a dynasty, like make sure that this family will last forever in time. So let's assume that this again, that we have a probability of activating a bond. So the grandparent has 1 kid, okay? So you have 1 bond here. The number of bonds that are at the next generation is z-1 multiplied by the probability of activating the bond. So this is the actual number of bonds in the 2nd generation. Then in the third generation, for each of those lines, you will again have this double descendancy. So you will have a certain power 2 here. And so at the generation number m, the average number of bonds is z-1 multiplied by p to the power m. And so if you want to have a dynasty that lasts forever, you want this quantity, when m goes to infinity, which is time, to go to infinity. In contrast, if you want to have a sol, which is not a gel, meaning that the monomers, they don't propagate, they don't connect to the full system, in that case, you want this to be finite or 0 even. So what is the threshold? What is the critical P for which you have this infinite behavior?
z-1.
Yes. So when P is bigger or equal to PC, which is 1 over z-1, then the gel is created. Meaning you reach infinity. You get the idea? So stated differently, if the grandparents have 1 kid, okay, you want to make sure that this parent at least will have 1 activated bond. So that is why there is z-1 here. Z-1 is due to the 2 remaining possibilities, but you want this to be bigger or equal to 1. So you want at least 1 bond. And then again, you want at least 1 bond to be created. So to make sure that the dynasty propagates, you want to make sure that there is the same number, there is same number of kids that are activated at each generation. Okay, so at least one bond activated. So that is good. So we can take two examples, Z equal 2, which is the trivial case. Z equal 2, PC is equal to 1. And you already got that intuition when we drew that picture here. Okay, so when Z equal 2, the critical probability is 1. You cannot have an infinite cluster with a probability smaller than that. And so it's really the maximum probability 1, and you cannot go beyond. So you are really, it's a very particular case, Z equal 2. So you're really at the limit. So for most other cases, so Z equal 3, for instance, you will have a finite probability that is strictly smaller than 1 and strictly bigger than 0. It's more interesting. It's a more reasonable situation. And so this is strictly in between 0 and 1. Okay. And all the cases after will be in such a situation where PC is a finite object smaller than 1. All right, so that was for PC. Now we would like to discuss the sol and gel fractions in my problem. So P sol and P gel, and to do that, we ask the following question. So we take a given monomer. So let me just draw again my favorite lattice when Z equals 3. And let me consider one particular monomer, this guy. And let me also consider one particular bond. Okay, I'm really taking one monomer and one of its neighboring, I should say link, not bond, the link. So just the line which is between this monomer and the neighbor. And I'm not, for now, asking or requiring this link to be a bond, meaning to be activated. I'm just considering the topology. Okay. So the question is, Q, what is Q? Which is the probability that this given monomer is not connected to the gel through this bond. So we can draw that as, if you want, it's just a drawing. I'm saying that I'm interested in the probability that this monomer is not connected to the gel through this particular bond. So does anyone has an idea on how to express a recursive relation on Q? Can do a partition.
We may look at the neighboring sides of the other extreme and say that
this guy, you mean?
Yeah, this guy.
Yes, correct.
And say that the probability of the first point not to belong to the gel.
Yes,
is
exactly.
that this guy, his neighboring sites does not belong to the gel.
Perfect. That's exactly the idea. So let us write that mathematically now. So I'm saying that Q, the probability that this particular monomer is not connected to the gel through this particular link, you have a partition of two possibilities. Either this red link here is activated, so it's a bond with probability P, or it's not activated with 1 minus P as a probability. Okay, so first we have this. So if it's not activated, that's it. It cannot be connected to the gel because it's not even connected through that bond. Okay, first possibility. Or there is actually a bond here, so it's more dangerous because then you could be connected to the gel. But as you say, now we can ask that none of those are connected to the gel. Therefore, you end up with independent probabilities that are multiplied, so Q to the Z minus 1. Is this what you had in mind? Yes? Okay. Is there any question on that? Is everyone with us here? Okay, assume it's a yes. Okay, so we found Q recursively. We have an equation on Q that we could solve for a particular Z value, for instance. So I'm not really interested in Q, I'm interested in P sol. P sol, remember, we wrote it somewhere. P sol is the fraction of monomers that belongs to finite size polymers. So it's the fraction of monomers that don't belong to the gel. It's not a good one. Okay. So what is P sol? It's the probability for a monomer, say this one, for instance, not to be connected to the gel.
For not being connecting to the gel, we need that with all bonds, it's not connected to the gel.
Right.
So Q power Z.
Yes, perfect. So we ask this guy not to be connected to that bond. This we already knew, but not to that bond and not to that bond. And those are independent objects. Okay, there is no loop. It's a mean field topology, as you remember. So it's really independent problems. And so I'm just multiplying the probabilities. Q to the power Z. Okay. All right. So if I'm able to solve this equation and find the solutions in terms of Q, then I immediately found the solve fraction for any value of P. That is interesting because I start to know more about the population in my system, either gel or so. Okay, so what is the equation satisfied by P sol? We have to answer. Well, then you just simply replace Q by P sol to the power 1 over Z. So you have the following equation. If I plug that into this guy, P sol to the power 1 minus 1 over Z. And in fact, I don't really need those guys. Okay, same here, it's useless. So I found the equation that will provide me P sol ultimately. So we can first provide some general features of that equation and then solve it in a particular case that is relevant. So first of all, there is this trivial situation where Z equals 2. It's trivial and at the same time is a bit specific, as we already discussed, because the percolation threshold is really at the limit of the domain where PC is equal to 1. So it's really that boring situation where you have a line and the gel is only when all the bonds are connected. So it's not very realistic. And you will see it's a bit strange in terms of properties. So when Z equal 2, which is this trivial case, I have the solution which is satisfying this equation. Square root of P sol is equal to 1 minus P plus P times square root of P sol, which is equivalent in writing that square root of P sol times 1 minus P is equal to 1 minus P. And so you have two cases. Either P is smaller than PC than 1. So remember, PC here is equal to 1. So P strictly inferior to PC is equivalent to P strictly inferior to 1. And thus, in that situation, I can divide by 1 minus P on the two sides, and P sol is equal to 1. So when in this very particular Z equal to case, if the probability is smaller than the percolation threshold, I recover the fact that the solve fraction is equal to 1. I only have monomers belonging to finite size polymers. This was exactly this region here. The solve fraction is 1 because I didn't reach yet the threshold for the appearance of a gel, an infinitely long molecule. Okay, so this is the trivial case. And now if P is equal to PC equals 1, then you see that those two cancels, and so any solved fraction is available. So in fact, it's because it's undetermined. If I plot P sol, it will be something like, so 0 is here, PC is equal to 1 is here. And so you will have basically this stuff at the exception of that final point, and then suddenly an undefined value because it should reach 1. Okay, so you really have a discontinuous function. That is this point plus a line that is not including that final point. And it's the same for the PGL. It's 1 minus that. So PGL will be, there is no gel, and suddenly, boom, there is this infinitely connected system. So that is why it's trivial, but at the same time, it's very singular. It's a bit weird. That is why we prefer to focus on situations that are more realistic, and z equals 3 is the typical one. Then they are all equivalent after that. And they are more complex to solve because this equation will become a polynomial equation with a very weird exponents, as you will see in a minute. So when you have, not weird, but I mean large. So when z equals 10, for instance, you have a 9th order equation. And so finding the solutions, as you know, despite the fact that you have constant parameters here, might be difficult. Okay, so when z is bigger than 3, then the solution should fulfill this equation. So P sol, I just rewrite here. And then there was this P sol to the power 1 minus 1 over z, if I'm not mistaken. Yeah. So first of all, is there an obvious solution to that equation for any z? And you can try 0. Yes, you can try 0 or 1, basically. Huh? Okay, so is always solution. I didn't say that it's a stable solution, but it's always a solution. But for z bigger than 3, there are other solutions. Because you have a polynomial now, depending on the order of the polynomial. So you have a polynomial here. So you see you have, for instance, z equal 3 means that you have q to the power 2. So it's an order 2 polynomial. So you have 2 solutions. So you have the one that we just found. That's the trivial one. P sol equals 1. But there is another one that we have to find. If now you have a larger order here, for instance, z equals 4, then it's a third order polynomial. Then you have 3 solutions, and so on and so forth. So we won't solve that for any z, of course. It's a difficult problem. What we will do instead is take an example, and I think it's the next question. Yes. So question number 5. So we will take the particular example where z equals 3. So in that case, this equation becomes pretty simple. It's q equals 1 minus p plus p times q to the power 2, which can be rewritten this way. Okay, and so we know that there are 2 solutions. The discriminant of that is 1 squared minus 4 p1 minus p divided by 2p, okay? And the 2 solutions are minus this term, so 1 plus or minus the square root of this discriminant divided by 2 times the first coefficient. Okay? And so if I write it in a complete fashion, I have this plus or minus 1 over 2p times the square root of, what do I have? I have 1 over, sorry. No, there's a mistake here. There is no denominator. Discriminant is simply this guy. right? And so I should write this here. Those are the two solutions. So I can just massage a bit this expression by enter, for instance, this guy inside the square root. So I have 1/4 p squared minus 1 minus p over p. And there, if I work on this, let us see. So we have the square root of 3 terms minus 1/p plus 1. And so here, we recognize 1 minus 1/2p to the square. Okay? So it seems that the result as the simpler form, is the absolute value of 1 minus 1/2p. Okay. So either this is equal to 1, or this is equal to 1/2p plus 1/2p, which is 1/p minus 1. So we found Q. There's two possible values so far. And thus we found P sol, because P sol, which is the thing we would like to calculate at the end, P sol is related to Q by the power Z, so by the power 3 here. So P sol has two possible values, either 1 to the power 3 or 1 minus P over P to the power 3. Good. So we are done almost. And we could now plot everything as a function of P, which is the control parameter, so between 0 and 1. Remember that since Z equals to 3, then PC is 1/Z minus 1, so it's 1/2. So PC is here. And those two solutions, we can plot them. So 1 is here. It's one possible solution. And there's another one here that we can compute. So let's take some particular values. When P is equal to 1, for instance, this is 0. And when P is equal to 1/2 here, for instance, 1 minus 1/2 over 1/2, it's 1. So it's here. And then for P smaller than that, it will diverge. Eventually at 0, it will be infinite. So you have a kind of, sorry, my bad, the wrong tool. No, it doesn't want. Okay, and I won't continue, but it diverges at P equals 0. So those are the two solutions. Then, of course, we haven't discussed the stability, but below the gel point, below PC, it's pretty clear that P sol is like that. We only have, there is no gel because the threshold was not found. And an argument for that is also that the fraction cannot be bigger than 1. So this branch is completely forbidden. Cannot exist. Fraction bigger than 1. And then you have now above this critical point, you start to have two solutions. So now think about stat-phys problems and easing models. You start to have a magnetization that appears. And there is one stable solution with a finite magnetization and one unstable solution with no magnetization. That's exactly the same phenomenology. We won't study the stability, but just we expect the behavior to cross over to this second solution. Yeah. So that's P-sol. And if I wanted to do P-gel, well, it's exactly the same, but reverse because there is -1. So there is no gel until 1/2. And then suddenly, boom, a gel until 1. And sorry, it's a bit sharp what I drew here. I should be more, there is not an infinite slope at the beginning. It's a finite slope. Anyway, it's the mirror of what was shown here. So just you see those curves, they kind of resemble a critical point. You have, think this is the magnetization, for instance, and you are dealing with the inverse of the temperature here. So when you reduce the temperature, there is no spontaneous magnetization, and at some point, boom, you start to have spontaneous magnetization when the temperature is below the typical Ising energy scale that you have in your model. And you have those kind of curves where a change of behavior occurs. And it's continuous, so it's a second order phase transition kind of, and we call that a critical point. Okay? So you can have fun and play with larger Z values numerically if you want. I think we are done for this part. Do we have any question on this already? No? Okay, again, feel free to interrupt if anything is not clear. And we will attack another interesting feature, that is the polymerization index. And in that case, we will restrict ourselves to situations where there is no gel. So we are approaching the gel point from below. In this diagram, we are really in this region, and we are approaching the moment where suddenly there will be a gel, but we are interested in describing this region. Not in terms of P-sol and P-gel, because we already did it, but more finely in terms of distributions. And in particular, I would like to know the polydispersity. For instance, when I'm approaching the gel point here, I start to have larger and larger objects in my system. I'm connecting more and more bonds, so the typical polymer chains or the typical clusters that I'm forming, the typical animals that are in the system, they are bigger and bigger. And also they are more and more dispersed. We would like to quantify that because I can have almost infinite clusters near the gel point, but also I still can have, because the probability is only a probability, I still have some monomers that are not connected. Okay, it's a finite probability, but it exists. So the question is, what is the dispersity? How does my distribution of sizes look when I'm getting close to the critical point from below? So with values that are smaller than P. Okay, that's the question. So for that, we need some preliminary steps. So what is the average number of bonds per monomer? Let me call it like that. So what is, yes?
ZP?
Almost.
1 minus P.
Hmm? No, it was good, but careful of double counting. It's true. I take a network here.
Okay, so divided by 2 because
Yes.
when we got the second one.
Exactly. But it is a good idea. So you have this monomer here that is connected to Z friends. 3 in my drawing, as an example. So the average number of bonds is, for this bond here, is probability P that it becomes activated. this one as well, and this one as well. So I have P times Z. However, each time I create a bond, in fact, it involves 2 monomers. So it's double counted. So I should divide this by 2, not to count too many cases. Okay, that is correct. So that's the average number of bonds per monomer. Okay, so now let's take a reference situation where there is absolutely no bond. I'm taking the network completely empty. You just have the monomers, but I never activate one single bond. So P equals 0. There is a probability that is 0 to activate a bond. Question, what is N tot? So remember the definition of N tot, because here we have plenty of definitions. So N tot is here, is the number of finite size polymers per the number of monomers. But when P equals 0, the only finite size polymers I have are monomers. So N tot is the number of monomers divided by the number of monomers. Okay? So how many do I have? I have 1. I really have an assembly of monomers that are not connected. You have the links of the network, but they are not transformed into chemical bonds or activated bonds. So in fact, what you have is a collection of monomers, simply. That's the only molecules you have in the system, that those point-like molecules. And so there is one molecule per site. So that is why the density is 1. Yeah. Okay. Now I would like to estimate, or calculate. Remember, in the case where P is much, strictly smaller than PC. So that's my question. How can I do that? To do that, I can think about what is the effect of adding a bond in the system. So look at this drawing. I start from P equals 0. I have a pure monomeric assembly. Now, let me add this bond, because I'm considering finite P now. So I add one bond. How is the number of molecules in the problem affected? I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the 9th molecule is a dimer, in fact. So what is the connection between the reference case where there is no connection? There is no bond, where N tot is equal to 1. What did I do in terms of number of molecules? Before the creation of that red bond, how many molecules do I have?
If we start from P equals 0 when there was just no polymers larger than monomers, then we add all the bonds we have calculated in question 1, that is Pz over 2, and by each bond we add, we reduce the number of polymers by 1, and everything it's counted per monomer, and so P tot becomes 1 minus Pz over 2.
Perfect, exactly. So each time you create a bond, you unify 2 molecules that become 1 molecule. So you reduce the number of molecules per 1 unit. So since we already know the number of bonds per monomer, Pz over 2, well, for finite P values, this is exactly what you suggested. Perfect. Careful that we made sure that from the beginning that now we are dealing with the approach from below of the critical point. Because let me explain, if now I consider P equals 1, the reverse case. Everything is connected. So all those bonds, they are activated. Okay? And so on and so forth. Okay? So I have really a macroscopic gel, everything is connected. Now, if I remove that, I still have two infinite-like molecules. They are super large, those two sides, because I am at the thermodynamic limit, the system is infinite. The lattice is infinite, okay? So you see, killing or creating a bond in this region of the phase diagram doesn't change n tot, because I'm not changing the number of finite-sized molecules. So that is why all the argument you've proposed I reduced the number of molecules when I had one single bond. I reduced the number of molecules by 1 unit. Only works because you don't have infinite-like molecules in the system. Okay, just a sanity check. All right, so now we are at question 4, I think. We would like to calculate the number average polymerization index, NNP, again for P smaller than PC. So remember, we had an expression for that, I think, somewhere. No, this was an example. Here, NNP is provided by P sol over N tot. And what is P sol? Remember, I am below the gelation point, so there is no gel, so P sol is equal to 1. All the monomers belong to finite size polymers. And I just found N tot, which is itself a function of P, which is 1 minus Pz over 2. Also, since I'm writing things in a general fashion with any z, I can remember that PC is the maximum probability, is the threshold value. So I should remember its expression, which allows me to write that z is equal to 1 over PC plus 1. So I can transform that into something which only depends on PC. I forget the specific topology of the lattice and to focus on P and PC, right? The important quantities. So I get 1 minus P over 2 minus P over 2 PC. This is the number averaged polymerization index. Okay, so I can take examples. Z equal 2 is the trivial case. When Z equals 2, remember PC is equal to 1. It's very particular. So I have a 1 here. So NN is 1 over 1 minus P, if I'm not mistaken. P over 2, yes. And thus, this quantity, when P goes to PC, which happens to be 1 here, this quantity tends to infinite. That's a very specific situation when Z equals to 2. Because when Z equals to 2, the Sol fraction is 1. There is no gel, but suddenly, sharply, when you reach the threshold, boom, everything is connected to the gel, and you have immediately one single molecule with an infinite number of monomers in it. And so the average size becomes infinite. I mean, the polymerization index becomes infinite suddenly. So that's particular. In contrast, when Z is more reasonably bigger or equal to 3, then the previous expression can be written here. And since PC is smaller than 1, in those cases, yes, it means that the divergence point will occur for P larger than PC. Okay, so this remains finite. Okay, what else? Now we go to the weight average. So it's question number 5. And to do that, we will again introduce this recursive trick. And we will introduce R. So let me just quote the topic. R will be the average number of monomers that are connected to a given monomer. Okay. Through one of its neighboring. Okay. It's also specified. So let me just draw it. It will be simpler. I have my network. It's an assembly of points with possible links. Okay, and I'm asking the question, let me take this guy. So connected to a given monomer through one of its neighboring link, this one, for instance. What is the average number of monomers connected to this guy through this link? Any idea for the recursion?
So there's 2 ways. So first, there's the fact that if there's no bound, it's 0, 1 minus p times 0, plus the probability that there's a bound, so p, times 1 plus, because there's this monomer, plus z times the average size per bond. So R.
Is it Z?
Z minus 1.
Yeah. Exact. Thanks. So let me re-express what you said. So the average number of monomers that are connected to this guy through this link is 0 if this bond doesn't exist. Or if it exists, that is why there is a probability P to activate it. First, there is one more. And then for each of those 2, which is Z minus 1 here, legs, I have R, which is the average number of monomers connected to a given bond to this guy. Okay? Any question? Baptiste, I heard from you.
Oh, no, sorry.
No, sorry.
Oh, it was unmuted. Okay, sorry. Okay, so I can transform that into R factor of 1 minus P Z minus 1. That should be equal to P. And here you recognize P over PC, right? It's P over PC because PC is 1 over Z minus 1. So I found the result for R. It's P divided by 1 minus P over PC, which in particular, at the critical point, explodes. So the number of monomers that are connected to this guy through that link at the gel point, at the transition point, is suddenly reaching infinity. Okay, that's expected. That's the physics. Okay, that's R. I'm not really interested in R at the end of the day. I'm interested in NW, which is the next question. Okay, so I want to study NW of P. And again, NW is the number of monomers belonging to a given chain on average. So what is NW? It's the average number, sorry, of monomers belonging to.
Starting from a side, we are looking to the average size of the polymer it belongs to. So this polymer is 1 himself plus R, which is times the number of bonds. So 1 plus the R.
Perfect. So again, NW is the average number of monomers in one chain, one given polymer, weighted by the mass, okay? And so we know now that typically this guy, through this bond, is connected to R units. So now I take the monomer I'm considering. In my lattice illustrated in the particular case where Z equals to 3, here is my lattice. I know that this monomer is present, and then it's connected to R guys in this direction, but also R guys in this direction, and R guys in this direction. Thus the Z times R. And so that gives me the typical size of the typical number of objects in an average chain. From the point of view of mass, from counted with weight, with a weight that is proportional to the number of units inside. Okay, so now I have the formula. I can just express it as 1 plus Z times R, and R was P over this divergence. And so this is 1 minus P over PC plus Z times P, and Z is we can express it from PC. It's 1 over PC plus 1. So that is Z times P, because there's this P here, and then I divide by a common denominator. Okay, so what do we see here? We have P over PC and P over PC. So this, due to the minus sign, cancels out with this. What else do we have? I think, no, there is nothing else, in fact. P1 minus P over PC. This is NW. And so when P goes to PC near the critical point, well, this is nothing particular, it's finite, but the denominator goes to 0, so it diverges. So no matter Z here, the weight average explodes. In contrast, for the number average, if you remember here, it was infinite in the Z equal 2 case, which is very specific, but in general, it was finite, since the divergence was occurring beyond the critical point. Okay, so the polydispersity should diverge then. So we can define it. Remember the polydispersity rho, careful with my notations between rho and P, and it's been bad, is this guy. NW of P divided by NN of P as we defined it previously. That's the polydispersity. And so if I use the previous expression, it's 1 plus P 1 minus P over PC. That's this part. And NN, where do we have it as a general expression? This is 1 over 1 minus P over 2. 1 minus P over 2 minus P over 2 PC, right? 1 more P over 2 PC, yeah. And so when Z is equal to 2, both quantity diverge, so there might be a cancellation, or I mean a finite ratio. Let's examine that, it's not clear yet. So when P goes to, so in that case, PC is equal to 1. So rho is 1 plus P divided by 1 minus P. Those are P. Huh? 1 minus P over 2 minus P over 2. So 1 minus P. So this cancels this out. And I have 1 plus P. That simply goes to 2 when P goes to PC. Because PC is equal to 1. So it stays finite. So you see, you have some polydispersity in the system at the critical point, but it's pretty reasonable. So you have infinite chains, but you have finite chain, and you have, in fact, you have an infinite number of finite size chain when you reach that point. But you have at least one chain with infinite number of monomers, and so this is counted with the same, weighted with the same price. In contrast, when Z equals to 3 or larger, as we saw, this was finite and this was diverging and this was finite, so this goes to infinity. So in a realistic case, and this is trivial, we don't care, in fact, in a realistic situation where you have a proper connectivity in your lattice, there is a very important feature at that point, at the gelation point here. There is an important feature is that when you go from below, you're reaching this situation from below. Of course, you don't change P-sol because you have not reached yet the critical point, so you still have purely finite size polymers, but the polydispersity is growing and growing and growing. And when you reach that point, boom, you have an infinite polydispersity, meaning you have all sizes present in the system, including infinite size. Okay, I think this is it for polymerization. And now we would like to end up by discussing the really the critical behavior and the objective now is to, can we discuss the shape of this guy when P goes to PC. So we will just, we will do it with some particular trick, as you will see, and do it from the point of view of combinatorics. It will involve counting, factorials, and so on, and we will do that together exactly. And then, using the Stirling formula as a homework, you will have the task to try to reach the asymptotic expression near the critical point. But I will provide you the main basics before that, and we will do it together. Okay, so the program is really to close the loop. We want to finally find the complete distribution of objects. Not only the dispersity, not only the P-sol fraction or the P-gel one, but really the full distribution that contains every information you would like to know. So it's, if you want, the solution of the percolation problem in the mean field case. All right. So for that, I will introduce a trick that I found very smart, which is the following. So I will change a bit the view and consider a monomer as a kind of molecule. So let me just draw first my favorite Bethe lattice in 3 dimensions, meaning with 3 neighbors all the time. So this is how I picture my gel. Okay, and then I will change a bit the view, and I will consider that this monomer is not only a point, if you want. I just say it's a kind of little object, like if you want a water molecule, that has 3 legs. Okay, same for this guy. And this water-like molecule can sometimes, but not always, create an hydrogen bond between those 2 molecules. It's probability P. So it's exactly the same problem. I haven't changed anything, but I'm just introducing a concept which will be useful in a minute of unreacted group. And this is a bond or a reacted group. Okay. So now you can picture the monomers not as real monomers, but as small molecules that can sometimes assemble to other molecules. Okay. It's just a change of vision. But now I will be interested when I have a given molecule, let's say this one, when I have this red molecule. Well, we see on this drawing that there is red parts and black parts. Let me even color the black parts like that. So you have 1, 2, 3, 4 unreacted groups. And you have 1, 2, 3, 4, 5 bonds. So now, each time you consider a finite size polymer, which is the quantity we would like to discuss, and I mean the distribution of which we would like to know, small n. In fact, we have to know 2 things that are related. We have to know how many red parts you have inside and how many green parts you have inside. And of course, I could have really exchanged the 2 here and say, well, the red is in fact here and the green is in fact here. That's another way of organizing the unreacted versus reacted links. So that's another possible polymer chain in the problem with same properties. It still has 1, 2, 3, 4, 5, 6 monomers, so it's a 6-mer. I should have said that from the beginning. Here, n equals 6 in this particular drawing. Okay, so you see there's a kind of combinatorics. How many ways do I have to pick the green among the green plus red? Okay, and so this will allow me to count the number of possibilities for a given P, which is the probability of a reaction. So that's the main trick I will rely on. And now I would like to first ask the following question. How many unreacted groups are there in a given n-mer? Okay, I'm asking what is the number of unreacted groups
Z minus ZP.
the given, okay, give me a minute, given n-mer. So you said Z minus?
ZP.
Z minus ZP, so Z1 minus P.
Yes.
Not necessarily, because those, okay, I see what you have in mind. So you are counting, for instance, in this molecule. No, let me take a better drawing. In this molecule, you are saying, okay, 1, 2, 3, 4 unreacted groups, right? But be careful that in this drawing, I was not discussing what is belonging, what is doing, what is happening after. In fact, I'm noting that I was wrong here. There should be always green at some point here. I should finish all the drawing. So 1, 2, 3, 4 more. So it's 8 here. Okay. Anyway, those green stuff, they are not directly connected to black monomers. They are first you have non-activated links. So and then again, since it's not reacted, another unreacted group. So this link here, it belongs to 2 unreacted groups. Okay. So let me then. So we will see. Up. Let me take an alternative view. I first consider the total number. So assume p equals 0, as before. Just reference. When p equals to 0, how many unreacted groups do I have? I have 1, 2, 3, so I have z unreacted group per number of monomers. I know I'm discussing p equals 0 here, but I will subtract something in a minute. So the reference is p equals 0. So first, before connecting the red bonds, I know that I'm dealing with the n-mer here. And so the n-mer, I know that it has n objects. And before doing anything else, those n objects, they have a priori 3 in this drawing unreacted bonds. So a priori. But each time I will add a bond in red, I will remove 2 unreacted groups. So there will be number of bonds times 2. Okay. And what is the number of bonds when I have n monomers? I have a chain with n units. How many connections between units do I have? The standard.
n-1.
Yes. So okay. And so I end up with n times z minus 2 plus 2, which is different from that. Okay? Because we were neglecting the fact that bonds belong to 2 monomers, and that unreacted group is not the same as unreacted link, because the link, again, is between 2 monomers, so it's shared. So we should be careful with this double counting. And also in your proposal here, more importantly, there is no n dependency. Whereas we expect the number of objects to grow with the size of the polymer. When I have a huge polymer, I have plenty of branches of that polymer that are not connected. So I should have something which is linear in n in any case. So that's another important aspect that was missing. Okay. Anyway, it's not easy, so very good to try. Okay, so I know a first very interesting quantity. Now I would like to, so I go slowly because the definitions are important here. Now I would like to introduce a link. So the definition of a link. A link is either a bond. That's a new definition of link if you want, or an unreacted group. So with this terminology, this is a link. This is a link. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so now you see what I'm trying to aim at. I'm now trying to say that I have a certain number of little rods that I can either decide that they are bonds, and I should take n-1 of those, and the rest should be unreacted links. And now the question is, how many ways do I have to pick the green stuff among the sum of the red plus green? That's what is going on. That will help me to calculate the full distribution. So let us do that. So how many links, first there is this question, I forgot it. How many links are there in a given n-mer? So it's the sum of unreacted group and bond. So the number of unreacted groups in a given n-mer, we already know it from before. It's nz-2 plus 2. So let's just put it here. That's the number of green stuff. But then we want to add the number of bonds now. And how many bonds? We already discussed that. It's n-1. So this is the unreacted part, unreacted groups. And in the drawing, it was in red. This is the number of bonds. So I can recast this formula by factorizing n, z-1 plus 2 minus 1 plus 1. That's the total number of links. So if you want, this is my pool. I will now do a game and I will pull some green and red stuff from this pool. And this pool contains a certain number of objects, no matter their color. This is this number per monomer, per n-mer, sorry. All right, so now we can attack. We have defined everything. So we want to compute the probability that a given unreacted group belongs to an n-mer. So as usual, we have to be slow with the wording when we deal with probabilities. So let's draw it so that you understand. Here is an unreacted group. So I take my gel, or I take my my system, my lattice that contains a certain number of chains and so on. And let me say that I pick one unreacted bond somewhere. I put my finger inside the system and I find a region where there is an unreacted bond. So I know this guy is unreacted. So there is nothing on this side. My question is, what is happening here on the other side? What is the probability that this guy that I've identified belongs to an n-mer from here and here? So I'm really picking one randomly. I found it. And I'm just asking the question, is it belonging to a solitary monomer, or does this leg belongs to a quadrimer or a thousandmer? That's the question. And to address that question, I will do some combinatorics. So first of all, let me just state that now in an n-mer, I know a couple of things. The n-mer is defined by the following stuff. I have n monomers. That is a fact. I have n-1 bonds. That is something that is also very well known. I have, you knew it from before, I have nz-2 plus 2 unreacted group. Sorry, z-2 plus 2, oh, excuse me. My handwriting is bad. Unreacted, okay, groups. And finally, I calculated here, nz-1 plus 1 links that have been defined here. What is a link? Okay, so that's the, if you want, the definition of an n-mer. Now, I've currently have identified already one unreacted group because I picked it. So remains well, this n-mer belongs to a monomer, so there is n-1 monomers remaining. There is still n-1 bonds to create because I only identified an unreacted group. I don't know if there is either an activated or not bond nearby. The number of unreacted groups remaining well has decreased by 1 unit. So it is nz-2 plus 1 only, because I already have 1 here. And the number of links, well, I've reduced this by 1, so I reduced this by 1 as well. And the number of remaining links to be found is n-1. I already have 1 link here. I need to fulfill the rest. So now we will do the combinatorics and just calculate the number of configurations you have. And I will put the probability. Of course, small p is very important here. What is the probability of activating or not a bond? So let me call, for instance, UN, which is what we introduced here, which is, no, I didn't introduce it. So which is the probability that an unreacted group belongs to n. The one I just picked, the orange one, belongs to a n-mer and not a n+1 mer or a n-1 mer. Anything else. Okay, any ID. There is the probability aspect and there is the combinatorics aspect. So I need to look at here. I need to find n-1 bonds. This is my task list, if you want. So I need to find n-1 bonds. For instance, here I would need to create a bond here, and then perhaps here as well. So I have n-1 bonds to be found, and so first of all I need p. Those are independent objects. n-1. You see the binomial law appearing here. Then I need the rest to be unactivated. So I need 1 minus p. And how many unreacted group do I have? I have nz-2 plus 1, this guy. So the rest is not activated. And then how many ways do I have? I need to pick which are bonds and which are links. And so I need to pick the number of bonds, n-1, among the pool. The pool is the total number of links, -1 because I already have the orange one. So it's nz-1. Oh, sorry. I'm pretty tired. Okay. And so this is my notation for, perhaps you note it differently. It's the factorial of this guy and the factorial of this guy and the factorial of the difference between the two, which is exactly nz-2 plus 1. So So this is the combination. There is not an arrangement because there is no ordering here. No matter who you pick first, it doesn't change anything. And so you have this binomial like this is what we call UN. Okay. So I'm not yet done, but I'm getting there. Need a few more minutes. Now, I will introduce a quantity that I call M, which is the average number of n-mers per unreacted group. So it's the number of n-mers divided by the number of unreacted group. Okay, that's the definition. And remember, UN is what? Is the probability that an unreacted group that I picked, the orange one, belongs to n-mer. So it's the number of unreacted groups belonging to n-mer among the total number of unreacted groups in the system, since it's a probability. So you see, there is the same denominator between the two. So in fact, I can recast M as UN, but by multiplying by the proper denominator and making sure that I remove the denominator in UN that was not the good one. And in fact, this quantity, I think I know it, is the number of unreacted groups in an n-mer. So what is it? The inverse of that is the number of unreacted groups belonging to an n-mer, to one n-mer. So this is 1 over nz minus 2 plus 2. Okay, so I found M, and I'm not interested in M. I'm interested in a final quantity, which is, perhaps I should keep, we work here. So I'm interested in N, that's my goal. Remember, this is the number of n-mers per monomer. That's the definition of the distribution we are interested in. So compared to M, M is what? It's the number of n-mers, but per unreacted. So they have the same numerator, but not the same denominator. So it's M times the number of unreacted groups divided by the number of monomers, because I want this denominator. So M, we know it, it's UN over nz minus 2 plus 2. That is M. And then the number of reacted groups divided by the number of monomers. Well, I have I take a system on my lattice. I have a monomer here. What is the number of unreacted group? What is this guy for this monomer? For one monomer, how many unreacted group?
One minus p times z.
Yeah. I have z possibilities, and for this to be unreacted, there is a probability 1 minus p. So it's 1 minus p. And that's it. I mean, I found with this trick of unreacted groups, I found what I'm interested in, which is n, which is the density, which is the number of n-mers per site. And it is given by, let me recast everything, it's UN was here. So UN is this quantity. So there is 1 minus P, which has an extra guy due to itself. 1 minus P and Z minus 2 plus 2. P is unchanged. Sorry, there's a Z here missing due to this guy. So there's a Z as well. So P was Pn minus 1. All right. What else do we have? Pn minus 1. And then we have the combinatorics. So nz minus 1 factorial. And then be careful, there is this nz minus 2 plus 2. And if you look at the expression here, there is this nz minus 2 plus 1 factorial. So in fact, it becomes a plus 2 factorial. And all this factor is just should appear here. Okay. Okay, so it was a bit painful, but we are done in a combinatorics fashion with finite values for P, for Z, for N. We found the distribution. So you know the mean field solution to your problem. You know the full distribution of sizes in your system. Now, homework. You all know about the Stirling formula. So we would like to consider the limit where you start to have a majority of very large objects. It's an asymptotic description. You also would like to introduce a threshold, something like PC minus P over PC, that you want to go to 0. So you are approaching the critical point from below, and you want this to go to 0. And something should be conserved, and so you will maintain that product constant. That's a choice. And under those assumptions, please show that you end up with a typical shape, which is the following. Where we introduce n star, careful, it's not the same n star as before, it's a new notation, which is a function of P, which is provided by Z minus 2 over Z minus 1. It's simply an expression. But the important aspect is that it should vanish with, or explode with 1 over epsilon squared. Okay, please do that. It's purely a manipulation of Taylor expansions and Stirling expansion. Okay, Taylor expansion is for that, and Stirling is there. So you combine the two, and I'm sure you will do that easily. But please do it. The question or the important remark is what? Can anyone see the connection that I would like to make here?
Flory exponent?
No, not exactly. Also, you're kind of right, because we discussed the fact that the polymer exponents can be viewed in another world as critical phenomena in magnetism. So in a sense, you will be right somehow, but I'm really addressing a strong connection between the percolation problem that is here in front of you, and another very important problem related to magnetism.
So NPN is has no length scale when we approach the critical point.
Perfect. So let me rephrase. We are facing an object that really looks like something like a correlation length. Okay? something like a correlator in StatFizz, okay? So you have an exponential decay over the correlation length n star. So two spins on a lattice, when you are not at the critical point, they will talk to each other, provided they are not too far. If they are beyond the correlation length, they don't talk to each other, there is no correlation. That's the definition of magnetism outside the critical point. So we know that beside critical points, there is this exponential decay over a critical length that we call the correlation length, sorry, okay? At the critical point, the correlation length goes to infinity, meaning that any spin in the system talk to each other. At that moment, n star goes to infinity, so this cutoff factor, the exponential comes to 1. And so now you're dominated by the amplitude that was not very important previously. But now you're dominated with an amplitude which is a power law. And so you go from an exponential law at the critical point to an algebraic behavior. And algebraic is very long range in the sense of StatFizz. So spins are talking to each other on very algebraic-like scales, very long range. And so this expression is exactly the same mathematical expression that you would find in a mean field model for critical points in Ising-like systems, okay? So that is why people were very interested in that. And now if you think about propagation of belief or propagation of information on a lattice or in Facebook or everywhere on the web or in the brain or in the cellular objects, whatever, where you have points that can either be activated or transmit information, well, there is a strong connection between that and critical phenomena. And also, if you're a very good StatFizz guy and that you know how to compute plenty of things in the StatFizz community, well, you can transmit that into information and percolation problems. Finally, of course, this specific exponent and this specific behavior of the cutoff lengths, the correlation lengths here, are very specific to the model, the Bethe lattice, and so the mean field calculation. But what is interesting is that in a more general non-mean field approach, what you would get is still something that has the same shape. Near the threshold, the critical point, you will get an exponent, okay, same, different value, but an algebraic dependency, and a sharp function, which is not necessarily an exponential, with a certain n star that depends on p. And this is very generic. So that is why I like the mean field approach so much. Despite the fact that it is very difficult to calculate analytically when you start to have some loops and interactions and it's not mean field anymore. Despite that, what you obtain and what you will obtain as a homework contains the main essential information that any system, any model will have. And that's why we learn something here, I believe. Okay, it's usual with mean field approach. All right, I was a bit too long. I'm sorry for that. I guess we don't see each other next week. So we would see each other the week after. No. All right, any question before we leave? No? So bon appétit and see you in 2 weeks.
Thank you, bye.
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 Thank you. Bye.